Hi, it's PCB layout review time again. Haven't done this in a while, and this comes from the EEVblog forum from forum user SoFPG from Germany. Hi to all my German viewers, and has got this project and wants some opinions on a layout. And I thought, it's probably an interesting example, so we might learn a thing or two here, hopefully. So let's go through it. Now what it is basically an image sensor here. We've got an FPGA here, which is a little Mark X02 in a 32-pin QFN package here, and then we've got a little microcontroller up there. Don't know what that is, don't care, doesn't matter. And we've got a USB UART thing over here and a little buck converter over here. So this is not a finished layout. This is just like an in-progress thing that he did just to show, like, am I on the right track? And he talked about stack ups and things like that. Now I don't know the exact part used in here for this image sensor, but look, it's a little 20-pin BGA in here, 5x4 pins. The only equivalent pin out I could find for this on DigiKey, for example, looks like it's the right business. I don't know, like, I don't actually have the Altium files to actually load in the proper thing, so we'll just go from the posted image. But this looks like it's one of these image sensor things. He says it's low resolution, like it's like a low end camera, so 640 by 480 sounds pretty viable. So obviously doing some FPGA processing of the image taken from the sensor, probably in real time, doing some, I don't know, masking thing, or running some sort of image detection algorithm, or OpenCV, or one of those image algorithm type processing things. And obviously the microcontroller here just drives that with an I2C line. But as I said, this layout is not finished. So let's just talk about several things of like stack up and other issues to do with routing and component placement and stuff like that, because these discussions are always quite interesting. So let's go over and have a look at the board here. All right, so let's have a look here. Now, I'm not too concerned about the buck converter here. That's not really what I'm after. I'm more in terms of component placement for bypassing and layer stack up and just other general things. But actually, this layout for this buck converter looks really tight, by the way. I'll just mention it for a second. It's about keeping your loop area as small as possible. And here's the bypass cap, and the traces are only small, so I wouldn't have done that. And what's that? What's that down in there? Oh, you don't want, like, yeah, put a right angle in there with a chamfer. You don't need the chamfer, it's okay. Anyway, I'm not going to talk about the buck converter. Obviously, we've got a USB input over here, and then an SO package UART, serial converter. Looks like we have a trace length matched trace here for the UART input. You don't necessarily, like, the distance here is so small, it's not going to really make a difference. But yeah, if you want to do it, decent practice. I don't know why everything else is surface mount on here, except for the connectors, and we've got a through-hole crystal. Why? I just would have used a surface mount crystal. Anyway, okay, so let's start getting into the layout. Let's assume that the placement of the parts is exactly where they should be. Obviously, the image sensor goes in the middle, and there's also this big, there's two big mounting holes, and it's obviously some bigger assembly that's actually assembled on that. So we're assuming that that can go under that, or is it? Yeah, because they're all on the top side, so there has to be space under here, because this shows this keep out for this module is like this. So I'm assuming that the components all fit under. So assuming that's all okay, let's just run with this. So just start with the USB UART chip here. You might think there's not much going on, and this is a 4-layer board. And he said he had to go to 4 layers because of it couldn't really route out the 5 mill, the 5 thou traces in between these pads in here. I'm going to assume he's got the pads fine. He's done the clearance rules and all that sort of stuff. He said he couldn't route those out on a 2-layer board using the JLC PCB manufacturing process, and that's quite common if you have a manufacturer in mind, and the 4-layer process tolerances might be different to the 2-layer process tolerances, and that could be a thing. So you just don't get the, you can't do 5 thou on a 2-layer, for example. I haven't checked that. Doesn't matter. Let's just assume that's been checked. And we've gone to a 4-layer. Now, ordinarily, a 4-layer board like this, luxurious. It gives you plenty of options for like controlled impedance traces if you need it, and good EMC and all sorts of stuff, and routing flexibility and everything. Absolutely fantastic. So the first thing is the stack up, which is the first question he posted in the forum. Now, for a layout like this, you might typically have power, and you'd have power and ground in the middle, and if you're running, it looks like we've got some controlled impedance traces here. We'll talk about this shortly. If you've got controlled impedance traces, the microstrip on the top layer routing, this is inner layer, but anyway, we'll get to that. Assuming it's on the top layer, then you would have then the next layer down. So the top layer would be signal layer. Your next layer down, the first inner layer, would be your ground, and then the layer below that would be your power. You typically wouldn't put signal, power, and then ground. It's still okay, but it's not quite as good as having the ground directly under it. Because then it changes your loop area bypassing and all sorts of stuff we won't go into. So top signal layer, ground plane, power plane, and then bottom signal layer. And that's generally how you do it. Now, the first rule of this is, and I see it over here, which we'll talk about in a second, and several other places, is that for a surface mount design like this, ideally what you want to do is try and route as much as possible on the top layer. So you want to avoid any vias jumping down to the bottom layers and things like that. So do as much as you can. Choose your component placement. Do as much of your routing as you can, all on the top layer. Only if you have to then jump down to the bottom layer, or even one of the inner layers or something like that, then you would do that. So anyway, so that's the thinking you should be going into when you're laying out a board like this. And he's clearly done that up here. Look, he's laid out this entire block up here, apart from this input trace going up here on the bottom layer, which is fine, even though that could have been done on the top layer. Look, that could have been routed around there and across like that, and there's no reason for that tight tolerance against the edge of the board there. In fact, some of the components are quite close to the edge of the board and has got rounded. I'm just going to assume that he wants a fully routed round edge board. There might be some fit to envelope reason for that, and that's fine, so we won't question that at all. But anyway, you can see that he's routed all of the signal traces all on the top without, so that's good. That's a reasonable buck converter layout. We won't worry about thickness of traces and actual in like real tightness of the loop area and things like that, so that's fine. So he's obviously had that thinking up there, and that is good. But you can see that that sort of thinking has like gone out the window here. Look, these are your serial. These are transmit and receive lines, okay? And it's immediately like jumped to the bottom layer here. Like, why? Why wouldn't you try and route? And why wouldn't you try and route your signal layers on the top like that? So I would typically, you would reserve your top signal layer for your signal traces, and then if you need, okay, this can't get through here because this power trace is going down here like this, but you could say that, well, all of your power traces, like these ones and everything else, they should probably be on the bottom layer, for example, the bottom signal traces, and then just pop up with a via there to come up, and then you've got all this routing room going through here like this to get your signals over. So really there was no need to drop that down there. And I know this, like, the board's going to work either way. It doesn't matter. This is not a complex route. It's more just getting in a good mindset of laying it out. So when you have to do a larger, a bigger, more complicated board, you're not going to come a gutser later by routing your power paths like this. In fact, on a board like this, you'd be routing all your signal traces first and then doing power later, except for the bypassing here and over here, which we'll talk about. I just moved my floating Dave head here, so it's like over that box. Anyway. All right, let's get back into it. Right, so let's assume that all the chips are placed like this. I mean, this one at a diagonal. This is a common technique if you're to mount your chip at 45 degrees like that. Don't worry about doing that. The pick and place machines can handle that just fine. There's no worries doing that. And for square packages like, you know, quad flat packs and QFPs like this one, if your chip was down right against the board, say you had like, you know, your chip down there like that, then you wouldn't be able to get all the pins out of the bottom in here. You'd run out of routing room. So it's common to turn them 45 degrees. You'll see that on large PCBs like graphics cards and like especially the older school graphics cards and things like that. You'll see like the main graphic chip with, you know, a big old school quad flat pack with, you know, hundreds of pins is just rotated 45 degrees. It just allows you to get your traces out at a, you know, a more reasonable angle. There's just more routing rooms. So anyway, after you've placed your chips like this, it's probably worthwhile placing your bypass capacitors because they're going to be important. And there's a bit of discussion about this on the forum and the criticality of bypass capacitors. And if we actually go into here for the Mark XO Lattice FPGA, Lattice have a specific power decoupling and bypass filtering for their programmable logic devices. And because this is a little kind of pissant FPGA, it's not, you know, a little piss weak thing. It doesn't require, you know, massive amounts of decoupling. It's only got 2 VCC pins plus VCC IO. So, you know, really VCC, you only need, like, this is not a big grunty FPGA. It's not going to take huge gulps of current like when you power the thing up, which some of your real big grunty FPGAs can, and then you need massive amounts of bypassing, and it's real critical and all sorts of stuff. In this particular case, like Lattice, you know, they recommend vary the use of 0.1, you know, 100N, 10N caps per device power pin is a good rule of thumb. So it's not critical, and of course I've talked about this as well. Beware of ESR and self-resonant frequencies, but you don't know that unless you have the specific simulation tools, and we won't go into that. For a little piss weak FPGA like this, you just like, you know, I'd just whack like, you know, 1 or 2 1 microfarad capacitors. Wouldn't even bother with any 0.1s or anything like that, or any 10Ns higher frequency ones. I'd just whack one large bulk decoupling cap through there, really. And it's, you know, they say it's going to eliminate the low frequency stuff. It's going to do the high frequency stuff too. You know, generally, maybe you might put a, you know, a 10N on there if you really want to. But anyway, this is not a critical design where bypassing is going to matter. We're talking about a tiny FPGA like this, and the image sensor, I don't know. I haven't looked, don't have the full data sheet for that. We've only got like a little brochure kind of thing. And these bypass caps are quite large, by the way. What are they? Like, they look like 0805 size with a large pad or something like that. Beauty. I don't hate those, you know, like 0402 rubbish or something like that, only if you have to. Anyway, so this is one of the main things I wanted to talk about with this design is the layout of these bypass caps here and here, but in particular the image sensor. This struck me. This is the first thing I noticed when I glanced at this image. I went, what? These are the bypass caps. He hasn't done any of the ground yet. This is obviously the ground side. This is the ground side. This is the ground side. Haven't stitched those through yet, which you should, by the way, just as a tip. When you're placing bypass caps and you're routing them in there as a first step, put in the via or vias you need for the ground and the power and things like that. Route those in, because then you'll know exactly how much room you've got to route out all of your signal traces out of here like this. Okay, so the first thing I notice is, why on earth is this trace running around here like this? This is the bypass capacitor. This is the bypass capacitor for this pin here. Wow. And this bypass cap is for this pin here, and this bypass cap is for this pin here, and this bypass cap is for this pin here. It's almost as if they've all been rotated, like they should all be rotated like 90 degrees like this. And this is one of the issues that you have. Like, you might your schematic of course, when you draw your schematic and you put a bypass capacitor per pin, it'll be C1, C2, C3, C4. And then when it automatically imports those onto your PCB, then you might go, oh, I'll just place the caps anywhere. And then your netlist will tell you, okay, this connects through to here. And you go, oh, okay, I've got to run a trace all the way. No, this is where you have to think from the get-go that component placement is everything. So especially in regards to bypass capacitors, just like this buck converter up here, you have to get what's called a small loop area. And that is the area from, say, this power pin here, okay? This has to go through this trace here, and that has to go through the capacitor, through some vias here, to the ground plane, and then back to the ground pin on the chip. I'm not sure which is the ground pin on the chip, right? But it's got to go through, and that is your total loop area, it's called, okay? And the larger your loop area, I've done videos on this, the greater your EMC issues in terms of like radiation and immunity as well. So the larger the loop area, the more problems you're going to have. So you want to minimize that. So this capacitor, so this pin here, let's say if we're bypassing this one, it should be this bypass capacitor here. And if it doesn't match the schematic, well, move it away and move this one here. So that this pad here is right next to here. Like this amount of distance is fine. You know, it's neither here nor there. So you simply route that directly through to there, and then it goes through and it goes through to the power pin. You see how much smaller that loop area will be? And if you take this example up here, which is absolutely enormous, look at this. This loop area is massive, and that goes through, it goes through your ground pin and up to here. Like, it's an absolutely enormous loop area. You may as well not even have the bypass capacitor in that case, really. It could even do more harm than good. So, yeah, really, I would, dedicate it. If you want to have 4 bypass caps for this image sensor, that's just fine. Just tie that one to there, tie this one to here, tie this one to, there's nothing on that side, is there? Then I would have put, so I'd move this one down to here, down under here, so I'd have one like that, and another one like that, and then run the trace directly down to the chips, and then straight through vias. I'd whack a via in there, 2 if you want, if you're really, really fussy. But yeah, a via there directly down to the ground plane, which is the layer just below it. And then you'll have the optimized small loop area for your bypassing. And then you've got the same thing going on over here. This one's a bit more awkward, but okay, look, this is the bypass capacitor for this pin. Okay, so that's exactly where I'd put it. I probably would have flipped it out that way, just so that you could route those traces out. Because look, right, you've already cornered yourself in here, right? By putting this here, and putting all these power traces in here like this, you've instantly created a bottleneck where you have no choice but to route this out through this via here and drop down to the bottom layer. There's no need to constrain yourself like that. So I would simply flip this capacitor and just move it in that direction there and have the ground pad over here, for example. And then you can get your traces out like that, and then route your power traces on the bottom layer. Well, actually by bottom layer, because we've got a 4-layer board, we would have a power plane. So you can use the internal power plane. That can either be a split power plane. I won't get into the intricacies of split power planes and split grounds and things like that. Let's just, and power plane usually shouldn't be a problem when you start to split your grounds up and things like that. That can be, generally speaking, be an issue. And once again, this power trace over here, it's instantly cut out all of these 2, 4, 6 traces, like this, 7 traces, okay? 7 traces that had to be routed out here. So you've prioritized one lousy power trace against 7 signal traces. And now you're forced, because you put that power trace in there, you're forced to drop all 7 like this down to the bottom layer. Now, So you wouldn't make that sacrifice. This is why I said route signal layers first and then worry about your power later, especially when you've got the flexibility of a 4-layer board. But now I realize why he might have done this. You see, we've got wiggle, 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 yeah, traces on here. These are to match the length. So this trace here matches the length of the one next to it. Now, you could argue whether or not that is required. I don't think that's required in this case. It might be required if you've got a real high-speed MIPI interface, for example, but I don't think this is a high-speed MIPI sensor. It's just a low-end 640 by 480. It uses the serial digital interface system. Oh, no, sorry, this is a parallel one. Sorry, no, I was looking at another one. This is like an 8-bit parallel output. You know, if you want to match the lengths and just because, that's fine. And generally speaking, though, you don't want to waste time like over-engineering something if it doesn't matter. If you want to, you know, muck around with your trace lengths and things like that, I know the tools can do them automatically and things like that, and it doesn't cost you a huge amount of time. But anyway, let's not worry about why the traces are matched like this. What you might be trying to do here, let's assume that you do match the trace lengths like this. You might want to match also the impedance of the thing. So you might be doing a controlled impedance, but these aren't, controlled impedance wouldn't be a thing for this particular design. But if it was, let's just assume if it was, here's the Saturn PCB calculator. This is a microstrip one where you've got the trace, oh, sorry, I can't draw on that. You've got the trace on the top layer and then the ground plane underneath. And that's a controlled impedance trace. Now, the one in the middle where he's actually dropped through to one of the middle layers here, because the bottom layer is blue and the mid layer is is the mid layer, which should be a ground plane or power plane. You could run these on the power plane, for example. Like you might want to run what's called a strip line like this, which has a ground plane up here, a ground plane up here, and your signal is sandwiched in the middle. Now, I won't go into the pros and cons of strip line versus microstrip. It doesn't matter, but that might be one of the reasons that you do that. But in this case, there's absolutely no reason to be running, to use one of your internal layers to do that. So yeah, I don't know what's going on there, right? I would have run all of these traces directly over there. Trace length match them if you want. I wouldn't have added this much wiggle in, but yeah, I would trace length match those. In fact, actually, I was going to say I would have chosen the location and the layout, the rotation of the FPGA here to match the shortest possible paths over to here. But anyway, so yeah, it looks like we got these 3 pins here which have to go out. That's just, yeah, another one over here. Is that another one? I don't know. So yeah, like there's a combination. Look, like this one here is going on the blue. That's going on the bottom layer. So you got that on the bottom layer, this on the inner layer. No, you want to follow that, you know, shoot for that holy grail of PCB layout goodness by having all your signal traces on the same layer, if you can do it. Avoid links. Holy grail of like single-sided PCB layout, for example, which SMD layout design essentially is. You're doing it like a single-sided design and then filling in the rest, you know, as I said, like the power and other stuff later with your other layers as required. But you're essentially trying to shoot back to old school single-sided PCB design with SMD components because they're not through-hole components. You don't have the luxury of essentially a via for every single pin. So really, so that's the holy grail. So I would have simply routed all of these as much as I could, as many as I could on the top layer. That would have been my first priority for this layout. Once I've chosen the location of my chips and I've put some bypassing around here and I've dropped the bypassing down to the power and ground layers, then we would have a whole bunch of empty space all in here and I would have routed out all of the critical data lines and the clock lines and control lines and things like that. And you'll find that once you get rid of this power trace, get rid of this power trace here, you know, maybe you might want to, instead of having the capacitor like that, you might have it like that, for example, or, you know, up here, for example, you'd have all this room in here completely free to route your traces across like that. And that's, you know, you want to prioritize traces, especially if they're critical, like potentially they could be if you had like a real high-speed, high-end image sensor with, you know, you might have to trace length and, as I said, controlled impedance maybe, or you got some other thing, you're running your DDR memory or whatever you're doing. And, you know, things can get a little bit critical. So, yeah, rather than just, like, use vias just to drop everything down, like, you should not be, unless you're absolutely at wit's end and you run out of space, you shouldn't be running. So, we've got, yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, there's 9 trace length matched layers, so that's 8 data lines plus the clock or something like that. That's all good. But look, I mean, you've got something like this, right? You've got this blue trace, wiggle, 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 yeah, over to here, jumping up through a via onto a middle layer, over to here, back down to the bottom layer, up here, and where does it go to? Does it go to there? No, where does it? Is that? Oh, anyway, you know, it goes up there. There's no reason to jump this through signal layers, through multiple layers like that. Only, you know, a large design, you're getting right at the end, you're at your wit's end, and you can't possibly get, you've been working a week on this layout, you can't possibly fit this last trace in. That's when you got to go, you know, crazy buggers, which by the end of the layout, by the way, you should only be left with non-critical traces. You should be routing all of your critical traces first as a priority. So, as I said, all the data lines, all the important data lines, all the important clock and control lines, and the rest, which is miscellaneous stuff like this. For example, this microcontroller up here is obviously controlling the I2C on this chip. It's got like an I2C communication interface, which is where you set up all the parameters and, you know, things like that, and data rates and, you know, whatever you set up in the sensor. So there's two wires going over here, and look at how this is going, right? This is, oh, look at it. I hate these chips. Like that's a pad on the corner. Oh, evil. Anyway, yeah, look, it's going over here, and then it's jumping on to the inner layer, and then it's going over here, and then it's jumping to the bottom layer, and then it's going back to the inner layer, over here, back to the bottom layer, back to the inner layer, and over to here. Wow. Like, for starters, I could have continued to run that on the top, 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 and like, you know, like, so yeah, like jumping layers when there's no need to. Now, of course, because you would have prioritized all of your data lines coming over like this on the top layer, you know, you would run this around the backside, because an I2C line, be as long as you like, doesn't matter, it's not critical. And if the longer it gets, you just lower the pull down resistor, by the way, to counteract the extra capacitance of the line, especially so over a long trace over a ground plane or something like that. Anyway, so yeah, so I would have taken, these are the two I2C lines, I would have taken just both of those. Where's it going? Yeah, over to here. Okay, so it's a little bit annoying. I think it's, yeah, okay, so it's these two pins here. So that's annoying. But it's only 2 lines. So yeah, I would have, like, maybe you could have said, okay, oh no. See, if you just dropped a via from your bypass cap down to your power layer, you would have room potentially, but all your data layers are, so yeah, all your data pins would be routed out like that. So that's kind of annoying, and these two are just stuck in here. These, in this case, you would route those last, and because they're low priority lines, you would route them last. You know, they're non-critical. So yeah, you might drop those down to the bottom layer and then just have bottom layer going straight over there like that. But potentially you could have done it on the top, but I doubt it. Because you've got to get some of these around here. Anyway, so offhand, we've got all these vias here. Like, count how many vias we've got. I reckon we could have got away with not counting the bypass caps. We could have got away with a couple of vias there. You know, 3, 4 vias, something like that total, as opposed to all these sort of stuff. And we would have lowered our loop area if we had our bypass cap going directly in here, and a via here going directly down to the ground plane below it, and Bob's your uncle. So yeah, and you can just see all the messy business going on with all these power traces here. And then you know, once again, the same thing. You've boxed yourself in here and you've got no option but to drop these 4 signal lines down to the bottom layer and then route them out like this. I would have pulled these 2 lines early in the process, even though they're non-critical. Early in the process, I would have gone, oh, okay, both of them, so assume these are both lines. Let's do a larger trace, right? Both lines like this, I just would have routed those around the bottom there and up to there. Is that where they're going? Anyway, I would have like routed that first. You know, well, you know, fairly early on in the design process. Just get those over, and anything that needs power, then I would have, you know, well, you would have had the bypass caps done already. But anyway, by the fact that you've snaked all of these power traces around here, don't do that. The top layer should be for signal traces. So this just looks like your JTAG interface here for your FPGA, and like these traces here are going, you can see those, they're going off to, yeah, various ones. I mean, look, you've got this pin here, drop into the lower layer, going around like this. Oh, no, it's not that one, it's that one. It's that one there, dropping, going around like that, up here, around here, like that. I mean, huh? Why? When you could have just, as a priority, routed that straight directly in like that. I mean, you know, these bypass caps don't have to be here. I mean, this FPGA, you could have, like, yeah, once again, like, I wouldn't have rotated that 45 degrees. Maybe I would have put it, maybe, you know, there, something like that, perhaps. I don't know. Yeah, it's neither here nor there. Yeah, but the point is that, yeah, all the power traces on the chop, just don't do that. It's just, it kills all your routing room and leaves you zero flexibility and forces you to go on other internal layers and things like that. And unless you absolutely need to, you would not be running traces on the internal layers. Why? Because you want to dedicate them to a solid power and ground plane if possible, from a signal integrity point of view, EMC and all that. It's better to have solid power and ground planes. And 2, you can't, like, check the traces. You can't cut them. You can't mod them. You can't, you know, do anything like that if you're dropping them down to the middle layer. So yeah, it's just much nicer, and you can't follow them when you know, if people have to, like, you know, repair, debug the board like that, you can't follow internal traces and things like that. It's just, unless you absolutely have to, and you wouldn't have to on a 4-layer board like this with just like, what, you know, 4 chips on it. No, you'd be looking to get 90% of this layout on the top layer. All of your signal traces on the top layer. 5 or 10% tops might drop down to the bottom layer. You'd have no signal traces on the inner layer. And there'd be no, even if you needed high-speed signal integrity, as I said, you would go for your microstrip, which is the controlled impedance on the top trace and the ground plane underneath. Or you could do it on the bottom layer, for example. But then you'd have to swap you'd have to trade off the ground plane on a lower layer, or you could, you might have 2, you know, like the odd design, you might go with 2 grounds in the middle and then run if your power requirements are simplistic, which they are for this design, you might run your power on your top and bottom. For example, you might have like some flood fill power top and bottom. Yeah, I wouldn't say I've never seen or done that in specific circumstances, but generally no, power and ground in the middle layers, and especially with this FPGA, which only needs the 1 power rail, which is 2.8 volts, there it is, for the, no, 2.8 volts is for the image sensor. So I think 3 volt, it might be running the micro from this, is it the same? Yeah, it's the same power. Yeah, it's the same power. And in terms of power distribution, look at this, right? Here's our output. I don't know why you'd run it like that and then around, like you would just run it straight into there. Like that, okay? You would have, well, you'd run it into your cap, okay? Because the capacitor here, this is your output capacitor, this is the inductor, okay, if you switch in regulator. This is your output capacitor. So this becomes your star ground, and then you would have a trace running out there to power this chip. You'd have a trace running out here to power your image sensor. You'd have a trace running out here to power your microcontroller. You'd have another trace running out here to power your FPGA. And, you know, you might run those on the bottom layer. But that's only if your electrical circuit requirements dictated that you have a star grounding sort of thing. But for something like this, we could just flood fill the inner layer. The second layer from the bottom would be our, the entire thing would just be flood filled with our 2.8 volt rail there. And then it just drops a via, anywhere it needs to down to the power plane. So yeah, then you don't have to worry about star grounding, but then you wouldn't run any power traces at all down here. You would just stitch it straight down there. Now, I could waffle on about all this for ages. I think I've stopped. I think I've covered sort of most things that I wanted to talk about here. But yeah, you can go in depth down the rabbit hole. Now, this design is not that critical. It's not high speed. Yes, I know about signal edge rates and all that sort of stuff. But it's like the requirements for the performance requirements in terms of layout for something like this, even though it has an FPGA and people say, oh, you got to bypassing requirements and FPGA are ridiculous. No, this is a pissant little FPGA. It has a single rail. It has hardly any, power on surge requirements or anything like that. Something like this, 2 bypass caps would more than do it. You could, I've done the months in video about how some bypass caps aren't even needed. So yeah, you might get away with 1. It depends where the power pins are. If they're like here and here, you might get away with 1 bypass cap for your core voltage, your VCC, and maybe another bypass cap for your IO voltages, for example, and your IO voltages might have been different to your core voltage. For example, you might be running your core voltage at a lower voltage, but in this case, I've only got the single 2.8 volts. So the requirements for this, no, just 1 big ground plane. I wouldn't have any power traces on here at all. Take priority over the critical signals first, and then route your miscellaneous stuff like your I2C later and your JTAG interface down here. Route all those last, and things like that. And then you wouldn't have to use all these vias all over the place like this. So yeah, shoot for the holy grail of a single-sided layout every time you do an SMD layout. So anyway, I hope that's helped the OP there and helped some others with some general advice. I've done lots of videos like this over the years of general layout advice and stuff like this. But if you like this sort of discussion and like a look at sort of critique of a design, even though this wasn't finished, I thought this was just an interesting example, which brings up a couple of interesting points about layout. So I hope you found that useful. If you did, give it a big thumbs up. As always, discuss down below in the comments. Let me know what you think about the green screen talking head thing. I think it's better. I know there's some green fringe, and if I move quickly, you can see the green halo and stuff like that. Lighting in here is not perfect, but I think the green screen talking head works. I've been doing YouTube professionally for almost 10 years now. It's the first time I've got a green screen. It's got to be some kind of record. Anyway, catch you next time.